Yeah, so today I want to continue with the section 3 from DG algebras to infinity algebras first. So I want to give some definition to fix lambda a graded vector space. For example, the underlying graded vector space of some chain complex of the cohomology of a chain complex, for example. We will. So I'm going to introduce step by step the function to chain complex of this graded vector space and some of its operations, and use that to define function homology of lambda very explicit in a way that it is convenient for us. That will be known by CPQ. The vector space of k-linear maps. So they are multilinear operations with p inputs and degree. I'm going to use round brackets for the grade shift and degree q. Okay, so will be convenient. So I know that maybe many of you are familiar with maybe functional cohomology and maybe some of them less. So I will nonetheless then explain certain very, very basic things. So not really that much, just as much as we need. So if I take an element here, I really want to think of it in sort of graphical terms as an operation with p inputs and a single output, well, in a certain degree. So somehow want to think about this, for those of you who could maybe recognize a little bit in operatic terms. That's the first. So because this makes certain formulas more intuitive, I believe. So I will need to look at my notes because there will be a sign that will appear, but I can only remember when I'm working with this like all the time, and then I forget the sign again. It works. So for p bigger or equal to so again. So okay, maybe try this. To define the operation CP. I need to maybe check this very carefully, like not PQRS. It's not that I mixed them because something will be wrong. So I want an operation which is in the first. So by the way, I didn't say P is called the Hodgkin or horizontal degree, and Q is typically called the vertical degree. And P plus Q is the total degree of this Hodgkin chain. So in the first by degree, horizontal degree, we are going to lose one input and second by degree, okay? And for those of you know, I'm going to introduce one of the so-called brace preliminary structure for the brace operations. That's what I'm going to later. And this is just given by the natural composition of multilinear maps. So I'm going to write it like, so I have an operation like this. So I between 1 and p, so the number of inputs of p, and it's not a circle, it's a built-in circle for a reason that will become apparent in some moment. So if I have G and I want to compose in position I with f. I want to take here I minus y inputs, then y. I want to get now r inputs, then I plus 1, then p inputs. And essentially, I will define this as plus minus 1. The obvious thing that one would do to compose the operation f in position I with the operation g. Oh, sorry. Yeah, this seems to be all fine. Yeah, if I make some indices, sorry, since I've run in, I didn't have time to sort of get into the mental space needed to give a talk. So I'm doing it on the fly. R x equals 1 x p. Yeah, so I take not g f. So I use f to combine these r inputs. So g is here and f is here, right? So I combine these r inputs into a single input. Then I'm left with xi equals, so here xi minus 1 and xi up to p inputs on which I can apply the operation g. Now, just for completeness, there will be a sign that is not the full sign. Like, I forgot, if I didn't get it right, yeah, it is important. Would be that, I did a mistake when copying it. So there is this sign, okay?
So you say that the sign doesn't come from the monoidal structure like this?
Well, I will explain where it comes from.
Okay.
It comes from a place, it's just at the moment looks unexpected. Here I have the degree of the operation f that changes places with the first I minus 1 variables x. This accounts for this Kosul sign. And then there is a lot of other information. In a nutshell, this sign comes from treating this as part not of the endomorphism opera of lambda, but of its suspension. Yeah, that's where it comes from. So there is so this is equivalent to thinking about the endomorphism opera of the shift of lambda. Yeah. So by shifting, I get additional signs. And these are the signs, and you work them out correctly, like this. Yeah, so they have an explanation. That's maybe important to know. So they do come from the monoidal structure and the suspension operation on so-called radial. So this is. But I'm not going to talk about operands.
Okay, is it the same? Is like because you want like a cyclic object? So is the sign kind of?
No. The sign is think of it. I mean, I want to make a definition that involves some signs, and I want to hide them. And a way to do this is to work on the shifted vector space, the graded vector space implicitly. And instead of doing it, I just put another sign. Yeah. Sorry. Yeah. But so it has a conceptual explanation, but this will make so provided they say that you just need to correct that sign, make it right, and then everything is fine. So yeah. So what you should think here is that in position I, you want to plug in the operation f that has these are inputs, but you need to take care of the sign here when you evaluate. Okay, so that is what this operation does. This is now needed to introduce the following notation. I will write GF for the sum overall I in P of G composition I with F. So this is one of the so-called brace operations that exist. For those that you recognize it is what you're thinking. You might be just surprised about the sign. So there are several time conventions that you can use on defining infinity algebra structures, and all of this is related to having a preferred sign convention. Yeah. So the signs are important, but at the same time they're also secondary. Yeah. So think of this. It's all an artifact of wanting to fix a specific sign convention. So one can verify, for example, that if I have an operation by degree 2, 0, so this means it's a binary operation of degree 0, then M2 is an associative multiplication if and only if M2 raised with M2 equals 5. Yeah, so you see here is the brace operation. I just take the sum. So roughly this would look like M2 plus well, the braces would look just like this, in some sense, right? So you see that this would describe a possible associator of this operation, and now you see that if you need to have some kind of negative appearing when you evaluate on elements, right? So that you can really see it as an associator, and this will come from this sign. Yeah, that's why you need the sign. Okay, maybe that explains why the sign conventions are needed and why they are convenient. So in this type of formula, I no longer need to write down any signs. The signs are kind of recovered correctly from the more complicated sign. That's the advantage of this approach. So with this incredible amount of motivation, sorry?
Yeah, just in the definition of epsilon, I think that the summation is wrong, right? You have one is less than or equal to I, less than I.
Where's the I? Sorry, I. Yeah, not so J less than I. Thank you. All of this. Thank you. Yes, so this serves for motivation. So as I said, I'm sorry that there's no time to give more motivation for this. And A-infinity algebra structure on lambda is a tuple M. To write like this: M1, M2, M3, of operations of arity. So in position n, I have an operation of arity n and degree 2 minus n, as I explained last time. So total degree 2, which is same total degree as this binary operation, such that m lambda with brace equals 0. Yeah, so I'm sorry for this kind of motivation. So this is meant to tell you that this equation generalizes in some sense the associativity equation, but I actually did not define the brace operation for tuples, but maybe you imagine what this means. So this equation, in fact, well, maybe you're right. And then if this happens, you call lambda. Lambda is then an A-infinity algebra. So this equation encodes the A-infinity equations for all n bigger than or equal to 1. 0 equals, I put down 0 on the other side, p plus q minus 1 equals to n. You sum over all I between 1 and p, np lambda composition and position I q. That's what this equation means. So in other words, you fix a number of inputs on your operation and you consider the sum over all operations that you can build, combining exactly two of your operations here. to form an operation of that arity. So here, that's why, remember, when we do this composition and position I, we lose an input, so we want the P plus Q minus the input that we lose is the fixed arity we're thinking about. And we just sum over all of them, and we are supposed to get 0, and this is supposed to be reminiscent for you of this equation. So in this very, very algebraic presentation, you're supposed to think this is a reasonable generalization of an associative structure, but I'm sorry, this is not maybe ideal motivation. So for example, 0 is the same as M1 composition with M1, so that M1 becomes, so there's only one input, so put 1 here. So M1 becomes a differential. For n equals to 2, it tells you that the binary operation is a chain map. For m equals to 3, it tells you that M3 is a null homotopy for the associator of M2. So M2 is associative to a fixed global homotopy, and etc. Yeah, so you're supposed to think of this as encoding a system of as a coherently associative structure. So this is some,
Since one half of this conference is also called homotopy theory, is this the same as saying that the derived category for the vector spaces you have an algebra object?
yeah, this is in the yes. So this would be like I mean, a DG algebra is I mean, if you say it in the good way, so that A infinity and the G becomes the same, right? So in that sense, yes. This is yes, and E1 monoid in the derived category of, well, infinity category, you know what. So yeah, so this turns out to be the reasonable thing to do. Right. So we have these equations. So for those of you that already know infinity algebras and you know there are all these sign conventions and you wonder what sign conventions come out from that sign, these are the Lefebvre-Hasegawa conventions. Also good to know for those of you that already know about this. So remark, we identify DG algebras with infinity algebras such that n bigger than or equal to 3 is identical to 0. And also another definition, an A infinity algebra is minimal if M1 is 0. In which case, you can check using the equations that the binary multiplication is already associative. Yeah, but there is still the higher structure. Yeah, even though the binary multiplication is still associative. So underlying a minimal infinity algebra, there is a graded associative algebra. I also mentioned for those of you that know that there are different notions of unitality for A infinity algebras, and I will not discuss them right now or at all probably in the lectures. There is a suitable notion as well. There is a suitable notion of, I'll write it and then move off the board, continue read the top part, but there is a suitable notion of A infinity morphism between two A infinity algebras. This consists of various operations now going from λ1 to λ2 of arity n and degree 1 minus n. So F1 is just a map from λ1 to λ2 of degree 0, as you would expect, satisfying some equations that we will not need at this moment. They can also be written efficiently in terms of more general brace operations for multilinear maps. And then if you write them in this form, they are similarly natural as this equation you might have found to be the first time that you see it. So we say that F is an A infinity quasi-iso. So we define, so the equations of A infinity morphism are such that F1 is a chain map with respect to the differentials given by the M1s. So we say that F is an A infinity quasi-iso if F1 is a quasi-iso. And you can also here put iso, or you can also say that when lambda1 equals lambda2 and F1 is the identity of lambda1, say, F is called gauge A infinity isomorphism. F1 is called the linear part, so also called an A infinity isomorphism with identity linear part. I might say that maybe more often. Okay. Yeah, so this is some kind of very fast introduction to the theory, so to the basic definitions around the A infinity algebras. If you've never seen this before, it might be difficult to appreciate why this might be interesting. One reason, remember, was the theorem of Kadeshvili that said for a DG algebra, the homology of A admits an induced A infinity minimal A infinity algebra structure. And there exists I just dropped the notation, but well, it's clear this is now and this is an A infinity quasi-iso that even more can be chosen to induce the identity in cohomology. So it lifts the identity map in cohomology. And this we saw that this was suitably unique, which actually means unique up to gauge A infinity isomorphism. So you could think of the notion of an A infinity algebra as a more flexible variant of the notion of a DG algebra that is now going to be stable under basically quasi-isomorphisms of chain complexes of vector spaces. Yeah, so that this is so-called the homotopy transfer theorem. So this is a very useful thing. So we cannot normally, when we have a right structure and an isomorphism, there is a basic transfer of structure theorem that transfers along this isomorphism in the structure. And if you try to transfer along here, well, you can choose a homotopy equivalent between A and its cohomology because we work over a field, and then you try to transfer it. You will not transfer to a DG algebra structure, but rather to this minimal A infinity algebra structure. So this suggests that this is a perhaps reasonable notion to consider. In addition, for also others that, maybe for this is new, think about in that case, our motivation is, as I explained, it reveals homotopical information that is packed in A in a different way in the form of these higher operations. And this will be needed to prove the theorem.
If A is minimal, are there some gauge A infinity isomorphisms or not? Are there gauge A infinity isomorphisms?
Yeah. So there you can look up. There are many.
Okay.
Huh? Later. Let me do that later. Yes. So not. I mean. Okay. So. Consider this finite dimensional algebra. The module category. Well, this is not A is not good notation. This is a finite dimensional algebra. its module category has, I will write as 3 objects, writing in this repeated way, 3 decomposable objects. This is the Auslander writing quiver of this the module category. The simple module. So this is the path algebra of the one quiver module with the relation it's Q. So we have a self-extension of this simple module. So this is the self-extension, and that called epsilon. This square turns out to be bicartesian, and this is a witness of the fact that the square of this self-extension is 0. But as it turns out, if you, well, I didn't do this very well, but if you continue the picture, there is here an extension with 2 middle terms that I would call T. So this is to say that maybe you're interested in the derived auslander algebra of the simple. And then what I'm trying to explain is that its homology is isomorphic K epsilon T modulo epsilon squared. So then this one squares to 0, but T doesn't. Yeah. And this is now supposed to have an induced minimal A infinity algebra structure, and you can find one with M 3 epsilon epsilon epsilon. So this picture kind of suggests that 3 times epsilon may be related to T.
Is it collaborative?
Huh?
Is it?
Yeah, actually, you can compute it in that way as well. Right. And this is going to be like plus minus T depending on the signs. So yeah, so T, then again, change the degrees. This is degree 1. This is degree 2. Well, I mean, I told you implicitly when I told you what they are. And so this is degree 2. This is degree 1, degree 1, degree 1. So here's degree 3. The operation of degree 3 is so degree 2 minus 3 minus 1. So 3 minus 1 equals to degree 2. So these kind of type checks. Yeah. So this is some example of the kind of thing that happens. And indeed, this is quite interesting because if you put the power here higher, as a graded algebra, this cohomology does not change. So you couldn't recover this DG algebra in some sense just from its cohomology because it's just not going to work. Or this category, or there are many ways to formulate it. So the cohomologies, as we of course expect and know, should be too weak invariant. And the way to make the power here appear is the operation. Okay. Yeah. So maybe this is okay. Yeah. Thank you for the question. In fact, this is a good example to keep in, just to get an idea of how maybe this can work. And yeah, in examples from representation theory, there are many basic examples coming from so-called Nakayama algebras, where the visualization of this induced infinity structures is quite, for me, pleasant. When do I need to finish now? No, I lost track because I thought I started maybe 10:04, 10:02.
I think so usually we
10:02.
Yeah, 10, but you have 5 more minutes. So you have half an hour.
Half an hour, okay, so until 11:50. Okay.
Maybe, sorry, can you remark why do you know that T is non-zero? Or like, is this
Well, you need to compute that T is non-zero.
like kind of visually? Or it's just that there is this image and
Well, it has to do with that it's involved on the kind of part of the minimal projective resolution of the sample. Maybe this one would be one way to get to know that this can be trivial. But yeah, you need to prove it. I mean, there are other ways to check whether such a thing is trivial, and basically the lack of some things in the top suggests that this this is related to this. But
and epsilon squared is 0.
epsilon squared is 0 by
Because
virtue more or less of this.
Okay.
I see. And now, you want to explain what do I mean by virtue of this?
Okay.
It's kind of It's
No,
a
it
computation.
makes
It's not. I mean, you
Yeah.
can compute it also with the projective resolution, and then you know well you know,
It
one
makes sense.
dimension and degree 2, there is this
It's like a
existence.
simple, like a filling of a simplest. Like it.
Okay, so okay. Right. So now I need to include some brief reminders, so not that I miss up the signs. So now we go. This was section 3, so we go to section 4. Brief reminder on homological. Okay. So as before, I have lambda migrated vector space. And well, first I'm going to define 2 operations, at least on the right now, maybe 3 on the function. Well, I want to turn that into a complex. So the first operation that we introduce is to the basic have a bracket. Is you know, I want to get my PQRS to. And so what does this do? So in terms of the braces, it's some kind of commutator. And here I need to take the so-called shifted total degrees of f and g. So if I write this, so if I write for the total degree r sub f, this is vertical degree, this is horizontal degree. I need to take here the shift of degrees. Yeah, so this all has to do with this shifting that we can visit in some parts of the story. So this is the Gerstenhaber bracket. The Gerstenhaber square. So this goes to 2t equals 2t minus 1 q is given by just the square of f is just the self-brace. So this is no longer a linear operation. Through the road soon. Then the next thing I want to do is I want to introduce the option, the differential is this is called the Gerstenhaber square. And the function differential is what is it? Is function differential is well, now I need some data, so not just a graded vector space, and I want an M2 an associative multiplication. As you see, I'm not making any mention of unitality. It's just a multiplication, saying anything, but that's what I need. So I define this as the Gerstenhaber bracket is M2.
Universal order.
Huh?
Universal order.
Sorry, yes. This one? Okay. So I have a differential of by degree 1,0. So in the first input I add 1. So this has parity 2. So I need to go to p plus 2 minus 1, p plus 1, and the other side. So nothing happens. And Well, as it turns out, yeah, the fact that this is a differential by some relations satisfied. So, for example, the shifted option chain complex, which becomes a well, even without this guy, but it becomes a DDB algebra, and it's even what is called like a Eisenhower algebra. I later, maybe tomorrow, will introduce when we needed the cup product. But in the end, the fact that this first is zero goes down to that equation. Yeah, so you can check this to zero. This will appear. They'll give you the result. So that's the Gaussian differential, and then the Gaussian homology of the graded algebra. So now this is a graded algebra. Is the homology of this graded so yeah, this differential. This is called chain. So we should call it a cochain complex until we have a differential, right? Okay. Good. Yes, so this computes, as you know, in the maybe if you haven't seen this graded case, it computes a bigraded vector space of self-extensions of lambda as a bimodule. Yeah, so this is has similar interpretation. So it's a very natural invariant to consider.
You don't write H8.
Where
to H?
Sit here. I already here. I erased this. I want to go with this. I'm not here.
Okay.
Yeah, I did. Right. Okay. So,
Just a time, depend on him to
huh?
use the high operations for this.
Sorry, which sort of
Like to get the actual homology groups, you need the high operations.
No, this is not for a graded algebra. Graded algebra. It's not the Gaussian homology from infinity algebra. This is indeed a common confusion in this context, because you also sometimes want to have something of this form, and you can consider two types, as an infinity algebra or not. And here we are thinking just as a graded vector space with an associative multiplication, and then this is already defined. Okay, so this is my brief reminder on Gaussian homology. Yes, so yeah, in some sense from now on, this lecture and the next, I need to go a little bit faster in order to communicate maybe a reasonable amount of intuition of the proofs of the theorems we are interested in. So this was section number. This was section, sorry, what was the section? Number 4. So then I have now section number 5, the universal massive problem.
It was 3.
Sorry, what?
It was section 3.
It can be because you made the same correction yesterday, and there wasn't already a 3. Well, or it can be, I guess. I don't know anymore.
Just the 3.
Yeah, I'm lost. Yeah. Next section, previous section plus 1. Yeah. I. The universal massive problem. Okay, so now I want to tell you what this universal massive product is and why it is well defined. So to keep saying notation. So I have lambda minimal A infinity algebra. So recall that means M1 is 0, and this implies that M2 is associative. So in particular, I have an underlying graded algebra, so I can consider the Hodgson differential on the candidate Hodgson cochain complex. Now, we are going to suppose that this underlying graded vector space is what is called disparse. That means concentrated in degrees that are multiples of d with my fixed d equal bigger or equal to 1. Yeah. So for d equals to 1, there's no condition. So this discussion applies for arbitrary minimal infinity algebra for d equals to 1, and for d sparse ones for the 0. So let's say let's call it the sparsity degree. Yeah. Of course, this is not surprising because graded endomorphism algebras of these close rotating objects are disparse. Yeah, so this is why we're interested in. So for degree reasons, I let you this to compute. M lambda n is equal to 0 if n minus 2 is remember the degree to minus n of the operation is not a multiple of d. So in other words, I can really write my operation. I mean, this is maybe my higher operations, maybe not ideal, but of course I don't mean this is the binary one, but I mean I now skip everything in between. So not binary, the ternary operation, but skip everything in between. Then I have 2d plus 2. Right? Yeah, so these are the only operations that survive. Okay, so that is already of some my interest. So now let us look at which is the first possibly non-trivial higher operation. And now if we look at the A infinity equation, so the A infinity equations for n equals to d plus 3 tells me that maybe to not get just make it quick and not confuse myself with doing this and to the plus 2 sorry, I mean the d plus 2. This is just I dropped the lambda because maybe it's too much. The A infinity equations, this is d plus 2 minus 1, d plus 3 elements. So these are all the ways to combine to get operations of d plus 3 elements because there are not so many other operations that I can use because of the vanishing. And you see that the Hodgson differential is a commutator with the 2 that appears there. There is a sign. And because of the total degree of both of these guys being 2, their shifted degrees is -1. So -2 minus 1 is plus. So they're all in plus. So you can work this out. This is the Hodgson differential at n plus 2. Yeah. So you see a little bit the advantage of this presentation is that I can hide all of the signs and I can sort of manipulate in a relatively efficient way the infinity equation that if you unravel like this, they reveal other sort of information, but maybe it's, well, as Georg was saying, more easier to make mistakes, right? So now I can create a system to prevent myself to make mistakes, provided that epsilon was correct. Yeah, but at least I have only one position to correct a mistake, which is maybe advantageous. Right. So yeah, I mean, the conclusion, just to make it very explicit, means that n equals 2, which is operation of degree 2, and so 2 minus this is minus d. This is a cosine for the Hodgson differential. That's what I have written. So I get, and now I will, before I wrote braces, now I will not do, I will write like this for the class. I get a well-defined class in Hochschild cohomology of degree d plus 2 minus d, and this is called the universal Massey product of length d plus 2. I don't want to write the curly bracket because of course it would be now confused with the brace. Yeah? So I get the guy like this. This is an invariant of the A infinity isomorphism class of lambda. So Hochschild cohomology is functorial under isomorphisms of vector spaces because this is essentially an endomorphism algebra. That's like an operatic version. And then this turns out, in particular, from lambda to itself is invariant under gauge, like identical invariant under gauge isomorphisms. And so we get some invariant of this guy, right? So if my lambda is coming from a minimal model, this gives me an invariant of A. Yeah, this is the message. This is called a minimal model. Okay, so yeah, so this is now an advantage of working with the A infinity algebra structures, that I have access to a nice invariant of a DG algebra even, and in a certain sense the derivation of this invariant is quite straightforward. I also remarked that to get the invariance here, one use the sparsity, because the sparsity of lambda also implies that A infinity morphisms are sort of suitably vanishing in some components as well. All of that plays a role, but let's think of this. Yeah. So, moreover, then I take if I consider, so this invariant has a different property. So if I take the A infinity equation for n equals 2d plus 3, right? Let me take this with me. 2d plus 3. Then I obtain 2d plus 2 plus m 2d plus 2 m2 plus n d plus 2 raised n plus 2. Yeah, so this will be, for example, 2d plus 4 minus 1, 3. And same here, 2d plus 2 plus 4 minus 1, 3, etc. And then I see that this is the Hochschild differential of m to d plus 2 plus the Gestenhaber square of n plus 2. So the Gestenhaber square for elements of total even degree or in characteristic 2 descends to an operation in cohomology. And what this is telling me is that this implies that the Gestenhaber square of the universal Massey product vanishes. So it's an invariant where it's not a completely arbitrary Hochschild class of this by degree. It must have vanishing Gestenhaber square. So that's already also of interest. So what we see here is that by yes, again, we see the same thing, that looking at these equations in this way, this condition becomes more apparent. And in addition, we see also the role of the higher operations. Yeah, so we needed to exhibit this vanishing, we need one operation higher. Yeah, so this algebraically we see the importance of these structures. So now what I want to do with this is I want to translate the condition of being DZ cluster tilting into a property of the universal massive product of a minimal model of my DG algebra of interest. This is now 4, 5, 6. Something that one could call the unit theorem. And this somehow will show that in a certain way, the DZ cluster tilting condition is also quite natural, because I hope that you will maybe agree that the condition that will appear in the theorem is actually natural. So I have an A at DG algebra, and I want to get things, so conditions on the DG algebra that are implied if A is a DZ cluster tilting object, the basic DZ cluster tilting. On a cohomology. So I put graded lambda in the cohomology of A, and lambda the degree 0 part. So this one should be graded, degree wise, finite dimensional, and this is now a finite dimensional algebra, and I ask that it is basic. I also want lambda to be this sparse, right? Because this is the vanishing of self-extensions for these DZ cluster tilting objects. And I also want that there exists a cohomology class of degree, well, I guess I here now will put minus D or its equivalent, an invertible class in this degree that comes from a fixed choice of isomorphism between T and its, the A and its shift. Yeah, it's default shift. So these are some necessary conditions to be DZ cluster tilting, right, for DG algebra, but they are not sufficient, and I want to find now a sufficient condition until 50. We said yes. Yes. Somehow I did that, and I erased it equally fast, or even slow, perhaps. Okay, so right. So yes, consider J the inclusion of the degree 0 part of the non-boldface lambda into the boldface lambda, so the inclusion of the 0 cohomology. This induces a map by restriction from the Hochschild cohomology of this graded lambda to the Hochschild cohomology of the degree 0 part viewed as a graded algebra concentrated in degree 0 with coefficients in a different bimodule than the diagonal. I did not define this, but the coefficients now are so every graded algebra is a bimodule, a graded bimodule over the degree 0 part. So this makes sense. But actually, one can compute. Well, in particular, I can take J upper star of the universal massive product. This lives in the Hochschild cohomology of degree D plus 2 minus D of lambda coefficients in graded lambda. That is turns out to be isomorphic because this computes the bigraded vector space of self-extensions. So now computes of extensions. This computes extensions in the ungraded sense from lambda to the degree minus D part of this graded bimodule. This is a straightforward computation, right? And this is just so that you see this explicitly in terms of things that have happened before. So lambda minus D is the minus D cohomology of A. It is the home in the derived category of A from A to A shifted by minus D, which is isomorphic to the home from A shifted by D this. And now you see that here on the contravariant side, which is the right module action, I have an action of the shift. So this is the same as because of the isomorphism with A and this. This is the twisted bimodule on the right by sigma equals sigma phi for my choice. Okay, now there's phis that are not matching. A shifted by B. As we did before.
Do you want to provide x squared?
X d plus 2. Thank you. What?
No, it's 2, right? Because now you're shifting back then.
No. So this is x d plus 2 in the degree minus d part of this. So here I'm not shifting any. This is to explain why this is isomorphic to this twisted bimodule. Yeah, so I can cancel the d here by the isomorphism phi, but this is just a statement about this bimodule. It's not about extensions in the derived category anymore. Yeah. Okay. So now, surprisingly, I have enough time to write the theorem. So this class is called the restricted universal matrix product of length equals 2. Then we have the following theorem. This is in the first paper. Everything as above, the following are equivalent. 1, A in the derived category of A, the perfect derived category is basic D set cluster tilting. This is equivalent to this class. So this is the class of the universal massive product of minimal model of A. This is an element of X d plus 2 bimodal extensions 1 lambda sigma that we can represent this by an extension lambda 0 t, I don't know, let me write like this, p1, well, let me write correct, p0, p1, p2, p d plus 1, where all the middle terms are projected by modules. And 3, so 2 and 3 are easily now seen to be equivalent because this sequence exhibits this twisted bimodule as the d plus second fold CCG of lambda as a bimodule. So that I'm saying that under the identification of extensions and maps in the stable category, this induces an isomorphism of these bimodules in, right? Because maybe let me assume basic here self-injected. As we did in the theorem, this was already like basic assumption on the lambda. So if lambda is self-injected, so it's enveloping algebra. So I can pass to the stable category of bimodules. And this is going to be this a triangulated category with shift given by the co-CCG and inverse shift given by the CCG. So I can write this as this. So I can see this also as a map here. And this condition is equivalent to the invertibility of these maps. This is clear, I think, from definition of CCGs. So what we see is that we can translate this condition of being this cluster tilting, of generating the derived category in a very controlled way to this restricted universal massive product serving as a witness of the fact that lambda is twisted periodic with respect to the isomorphism that encodes the action of the shift, default shift on the additive closure of A. So A needs to sort of already witness this in this alternative way, the twisted periodicity. Of course, we rely on these theorems and the other things I explained before. But for example, if you found the definition of this cluster tilting a little bit strange, perhaps this is more natural if you come from the world of A-infinity algebras, because defining the universal massive product only requires this sparseness. I mentioned that for d equals to 1, we're talking for the number d plus 2 equals to 3. This is defined for all DG algebras, right? So this is a standard invariant that has also, in the case d plus 2 equals to 3, had been studied before, even also in the topological setting. But what we see is maybe this condition is not that surprising. I mean, it's somehow, from a purely algebraic conceptual perspective, is also natural and turns out to be equivalent to this cluster tilting.
In 3, that's an equivalent, right?
Well, I want to correct here, ISO.
See.
ISO in, sorry.
And the number 2 was it?
The condition that you can represent this by an extension with projective here, projective
okay.
bimodule. Sorry about the sloppiness. In principle, you can always achieve by standard computations that all except the previous one, the last one, are projective bimodules. So you have a question about this one. This will turn out to be projected, for example, on both sides and things like this. And here is where we use the field is perfect, because there is a criterion to check that the bimodule is projective by tensoring with arbitrary bimodules and so on. And there is what we will need. That criterion requires perfect, or the quotient of lambda modulo its radical is a separable algebra. So one can generalize a bit, but here is where we need the assumption of the ground field being perfect. Yeah, so there is kind of hidden in this thing, and to use that criteria, we use the relationship between being this cluster tilting, d plus 2 angulations, and just to conclude, such an eta with projective middle terms by the work of Amiot for d plus 2 equals to 3, or Lin in general. This thing gives you a d plus 2 angulation. So we use the interplay between all of these things. So the proof of this is kind of quite involved. It has kind of a lot of moving pieces. And it happens mostly, I mean, not completely because there is this invariant, but it happens mostly at the triangulated level. So, for me, okay. I'm finished.
Questions or comments for Gustavo?
Okay. So maybe like just so this an angular, like this is kind of the picture you get from those angulated.
It's related, yeah. So you can use this sequence to define a class of d plus 2 angles in the category of projective modules over lambda that are certain exact complexes with a connecting map to tensor into this that gives you the sigma minus. So this is the inverse suspension essentially. They need to satisfy some compatibility condition relative to this class. That's the way you proceed in that case. Yeah. So in a way, the universal massive product determines some class of d plus 2 angles, and you want to check that this is the same d plus 2 angulated structure, for example, that you will get from the DC cluster tilting thing. Yeah. So you use this imposed structure on the homotopy category, let's say. Compare these notions. Yeah. That is what is up. But this is unfortunately, this proof is quite involved, so I don't normally have no time to explain that in more detail. So it uses relationship between total brackets, massive products, these Hamioli triangulations, d plus triangulations.
So we can thank Gustavo again for his help.